Hello and welcome to the pre-lab video for the acid-base titration experiment, which is part of the General Chemistry 2 sequence at York College of Pennsylvania. The goal of this experiment will be to identify an unknown organic acid and we will do that via the titration of our acid with the strong base sodium hydroxide. If you've taken Chemistry 1, I'm certain that you have completed some titrations, and titrations are nothing more than a quantitative approach or technique to follow the progress of a reaction, to reveal some key point during your reaction, often the point when both reactants are present in equal quantities according to the ratio of the coefficients of your reaction. Okay? Now usually titration is used for acid-base reactions, but that's not always true. And again, if you completed Chem 1 at York College, you did a redox titration with bleach as part of your curriculum for Chemistry 1. So you're familiar with applying this technique to some other areas. One of the things you do when conducting a titration is usually to visualize the process and the progress of your reaction, and often you invoke an indicator to do that. These are the chemicals that change color when you reach the key point that you're looking for in your reaction. Okay? However, that's not the only possible way to visualize that special point. You could use any property or any measurable property that changes during the course of your reaction. Titrations can be followed via electrical conductivity in some cases, and via pH, which is how we will follow the progress of our reaction that we're looking at today. So let me walk you through some of the basics of acid-base titrations. Now, acids and bases come in different different strengths as we've studied in lab. And again, the strength refers to the amount of ionization that's occurring. We could have the reaction between a strong acid and a strong base. A strong acid, strong base reaction, if we followed its progress with pH, okay, so we were measuring the pH, the amount of hydronium ion present during the reaction, what we would be doing is adding the base during this setup. So we would have our reaction flask, okay, or our Erlenmeyer flask usually, and you would begin with your acid in this flask, and then you would most likely use a burette to add your base. This is the same way that you conducted titrations in Chemistry 1, I'm sure, here at York. And so now we would just do this a little bit differently in that we're going to measure the pH each time we add some base into the acid. At the start, we have a huge excess of acid, H3Os, so that pH would be very low. And that would stay that way for a very long time. And then all of a sudden, as we reach the molar equivalency between the two, the pH would rise very rapidly, and then it would flatten out again when we have our excess base at the top. Excess base, excess acid at the start, and so right in between them, at the point of inflection, where the pH is rising most rapidly, is what we call the equivalence point. It's often also referred to as the end point of your reaction. In Chem 1, that is where you stopped. You never saw this second portion of the reaction, because this is where your color change would have occurred for your acid-base titrations that you did in Chem 1. Now when you use a strong acid and a strong base, the H3O and the OH minus form water. Actually, it would form two waters. And so if these two are present in equal amounts, they're both completely eliminated, and you have only pure water at your equivalence point, in other words. Okay? Which means the pH of this type of titration is 7 at its equivalence point. Okay? Today's reaction, though, will not feature a strong acid, but rather a weak acid with our strong base. So what will change? We'll still follow the pH as we add our base. Switch to green, I think it's showing up a little bit better. We'll have extra acid at the start, but now our pH will not stay rock solid low like it did before. It will rise steadily, but not rapidly like it does here, okay, for a short period of time. Then we will reach a point when it does rise rapidly and we end up with our excess base, just like we did in the original case. Okay? Now, this is owed to the fact that our weak acid, HA, when it reacts with our strong base, produces some conjugate base, A-, and some water. As we'll, perhaps you haven't covered it in the lecture yet, but we will be covering it shortly if you have not yet covered it. When you have some of each of these present, so we haven't maybe used up all of the HA yet in this portion of our work, and we have some A- forming, we have what's called a buffer solution. And it's intentionally trying to resist the rapid change in pH that's being brought on in this section of the titration. Okay? And these actually are some important characteristics of our weak acid, strong base titration. And it's how we will identify the unknown acid that we're working with in today's experiment. So there are two key points on this titration curve. The first is again the equivalence point. The equivalence point of this titration curve will not have a pH of 7, because at the equivalence point here, if the moles of our acid and the moles of our base are perfectly equal to each other, which they are, these will both be canceled out. However, we'll have created the condition, so these are completely gone. We will have created the condition of now a weak base hanging out in water, which can have an equilibrium that forms some HA and some OH-. So there's a little bit, it's actually driving a little bit of the reverse of this reaction, in other words. And so there's a little bit of OH- produced, which raises the pH to some value greater than 7. Okay. But the key of the equivalence point is that the moles of the acid are equal to the moles of the base. And that's worth stopping at this point and talking a little bit about the pre-lab questions. The first pre-lab question asks you to use this point to identify the concentration of one of your components of your titration. So at the equivalence point, always it's going to be true for a 1-to-1 titration that the moles of acid equal the moles of base. When both of these are in the form of a solution, it's easy to express these mole quantities as the products of their molarities and their volumes. And so if you don't know one of these 4 values, you can use the other 3 to find it. And so in pre-lab question 1, you're asked to find the molarity of your acid that you're working with when it's used to titrate a base. So the molarity of the acid would be MbVb, the molarity of the base that you used, divided by the volume of the acid. So in this case we used 0.120 molar base and 26.12 milliliters, which I'll convert to liters. and we divided that by the 14.6 milliliters, so 0.146 liters of acid. This gives you a molarity of your base, or sorry, of your acid of 0.215 molar. You've actually done this titration before in Chemistry 1. It was part of the standardizing approach when you standardized your sodium hydroxide. This will also be a key component of this laboratory. You will standardize your sodium hydroxide via a strong acid, strong base titration. Now we can also use this point to backtrack a little bit in a different way. So if one of our components was not in a solution, but rather came in as a solid to this reaction, we could still use the end point, the equivalence point, to calculate some important details. And pre-lab question 2 gets to the heart of this. We have a base of a known concentration. We measured out a certain amount of it to titrate an unknown acid. So what is the molar mass of our acid? So think about what molar mass is. Molar mass is the mass of a mole. Translate that into a sort of a formula. The mass per mole. So it's the ratio of any mass quantity to the equivalent mole quantity of that substance. Well, we can use the titration relationship to find moles. And that's what we're doing in pre-lab question number 2. The moles of base are found from the MbVB. We're given them. And I'm not going to do anything with the left side of this equation, because I'm going to use the base to tell me how many moles of it were present at this endpoint, which must be equal to the moles of acid present at that point. Okay? So it's sort of an indirect way of finding out how much acid we had present. So 0.164 molar times the volume, 0.02230 liters. And this gives us 0.003657 moles. Okay? That will now become the moles of our acid. Thus, the molar mass of our acid can be found by taking how many grams this sample was. So we used 0.283 grams, and it's now divided by, we know it to be 0.3657 moles. So the molar mass of this unknown acid is 77.4 grams per mole. This should also look pretty familiar since it was part of the acid-base titration experiment in Chemistry 1. Okay, so a lot is the same as what we did in Chem 1. The difference is that we're visualizing the endpoint through a different technique in today's experiment. All right? So you'll get your molar mass of your unknown acid. Now there's another important feature that comes off of the titration curve. And it's in this buffer region. So at this point, at the end point, which is where I would get the volume of the base that I used in the questions that I just answered over here, the moles of acid are equal to the moles of base. But if I went backwards to half of that volume, okay? That's what we call the half equivalence point. At this point, the moles of base added, well, it's not totally equal to the moles of acid present. It's only 1/2 the moles of acid present. But this is kind of unique, because if we've added a quantity of base that's half the moles of acid, we'll have eliminated half the moles of acid as well that we started with. And so we'll actually end up with a condition where the moles of acid left, okay, are going to be equal to the moles of conjugate base formed. Okay? So our HA and our A minus are going to be equal, in other words. The concentration of our weak acid and our conjugate base will be equal to each other. One of the formulas we'll learn in our studies of buffers in chapter 16 is the Henderson-Hasselbalch equation. Which tells us that the pH, anytime we have, so when A minus and HA are present, okay, so anytime we have a mix of weak acid and its conjugate base, or weak base and its conjugate acid, this formula will give us the pH, where the pKa is the pKa of our weak acid. And these are the concentrations. Well, at this special half equivalence point, all right, the HA and A minus are equal to each other. So this entire fraction equals the number 1. And the log of 1 is 0. So this becomes pH at that point equals the pKa. So whatever your experimental pH is, that's why we're going to follow this throughout the reaction. Whatever your experimental pH is, it becomes the pKa of your acid. So you'll have two properties of your acid from this experiment. The molar mass, which you will derive from the equivalence point, and the pKa, which you will get from the half equivalence point on your graph. All right? And those two should be enough when you're given a list of potential acids to identify which acid you were working with. If they're not, we've made available in the lab the melting point analyzers and some capillary tubes. You can melt a small sample of your acid, just like you did during the melting points analysis experiment earlier in the semester, to get a third property of your material. And at that point, it should definitely be clear which material you are working with. Okay? So we're going to generate some physical properties of our unknown acid in order to identify it. Okay? And they'll come from the titration curve. Now, in practice, you'll do the titration twice of your weak acid. First, you will titrate your sodium hydroxide to standardize it. This will be very similar to the way you conducted titrations in Chemistry 1. You'll use phenolphthalein as your indicator. So you're looking for that clear to light pink color change to tell you when you've reached the equivalence point. You want to conduct 3 titrations that are consistent and giving you the same concentration of your base. Because you really want to know, as accurately as possible, that concentration of the base. Then you will do a rough titration of your acid, where you can quickly pour in, you don't have to generate a lot of points, but where you quickly pour in the base to your acid, watching the pH. So if you were to graph that, it would look more like this probably. You would have just several points, and there would be no line there. So you probably would not see the equivalence point, but you would have a rough idea of what pH it does occur at by looking at these 2 points in particular. Now you'll do your fine titration, where you can add in more dots. So the second time, you'll want to try to measure out a sample whose mass is very close to the first sample. Okay? If it wasn't, it would occur at a different endpoint. So that's key. They don't have to be identical, but you want them to be close. And now you'll go in and you'll fill in a lot more of these gaps. And then hopefully you would see something much more like that, that sort of draws out the curve. When you make this graph in Excel, you may use the connect the dot feature and have it add this line. This is not a trend line. This is the simple connecting of the dots with a smooth curve. Okay? You'll want to look for the biggest jump, and in the middle of that biggest jump, that's what you will call your equivalence point, and that volume is what would kickstart your calculations for determining the molar mass of your unknown, and then going to half of that volume and simply recording the pH at that half volume, which gives you the pKa, and you can calculate the Ka by taking 10 to the negative pKa. All right? So I think I've addressed most of the issues associated with the lab and with the pre-lab as well. The third pre-lab question asks you to explain how you're using this titration curve, so we've essentially done that. On a titration curve, you're looking for these two key points, the equivalence point and the half equivalence point, that can give you the molar mass and pKa, respectively, of the unknown acid. Okay. A couple of other things that I've mentioned during the pre-lab discussion relate to some of the discussion questions at the end of the lab. In particular, again, this half equivalence point and what it is, and also I believe there's another question that I've addressed. If you paid attention, you'll find that when you're looking at your discussion. Okay? With that, I'll wish you good luck in identifying your unknown organic acid, and an enjoyable time in the lab.